Yeah, cool. We always just like do these random tangents at the beginning, and they always turn out to be super interesting, but we never record it because it's like not the material that we were going to cover or whatever. But yeah, so I've been working through a Rust course on Udemy, and it's nice. I mean, it's just like just focuses on the Rust programming language. It's not, not related to anything else in particular. But yeah, I would love to talk about it because I feel like it's the language I'm like the least familiar with. So if I get too far away from it, like for a week, if I don't do something specifically with Rust, like I come back and I'm like, oh man, like how do I do this thing again? And then I remember pretty quickly, but there's always that like initial hesitation.
Yeah.
And it sounds like the Rust builds are kind of painful. Is that not true when you're not dealing with substrate or something?
Yeah, it's way worse in substrate, especially if you're referring to the compile time, like specifically how long it takes.
Oh yeah.
Yeah, that's bad in substrate for sure.
I mean, nothing I'm currently writing takes more than a blink of an eye to compile because it's just like a single main function and that's
exercises and stuff.
Yeah, maybe there's like 2 structs in there or something, and that's about all.
Yeah.
Some print line macros,
Yeah.
Yeah. So I said I wanted to talk about lambda calculus and specifically, I mean, if you guys are up for it, I'm up for the challenge of trying to like get everybody up to speed so we can talk about this like Scott-Curie undecidability theorem. It brings together a lot of things that I feel like I've heard about in passing. But again, as my experience with lambda calculus has totally been in passing, that's how I feel about all of this stuff. But it brings these things together.
What's the name of the theorem you're working toward?
Scott-Curie undecidability theorem.
Oh, is this the famous Curie from like?
Yeah. Oh yeah, definitely.
Oh, this is Haskell Curie. Yeah. Okay, cool. Undecidability theorem.
Undecidability theorem. Yeah. So it's basically, I mean, so the high level idea is kind of like okay, so you have your lambda calculus terms, right? And you can think about sets of these lambda calculus terms. And there's this property which we can talk about called being closed under conversion, and basically that means like beta conversion. So you can like do beta reductions or alpha conversions, like change the name of bound variables, and you can kind of like think about it as like beta reductions take you down, and you can do some alpha conversions along the way, and then like the top thing and the bottom thing would be like a beta conversion of one another. But it doesn't only go in one direction. You could also do the beta reduction sort of in the other direction. I talk about this thing called...
Is that what it means to do it in the other direction?
What's that?
Is doing it in the other direction, like unapplying functions or something, or saying like, given this term, here's some terms that could have led to it or something?
Yeah, so it's like, if I have some term A and it beta reduces to B, and then I know some term C that beta reduces to B, I would say that A and C are like beta equal. So there's this like equality relation called like beta equality. And those guys, and I could do an alpha conversion in there as well. Like that doesn't, spoil the bunch or anything.
So beta equality is like, it's saying like so if term alpha and, term A and B are like 2 different terms, and and if we say that they're beta equivalent, what that means is that like they both reduce to a term, either like the same term or terms that are structurally equivalent or something like that.
Yeah, by structurally equivalent, like alpha equivalent.
Oh, okay, yeah. Gotcha. And alpha equivalent means like they're the same except maybe like variable names or something like that.
Yeah, bound variable names can be changed in a consistent way, of course.
Okay.
So you're saying this is more strict than by simulation, right?
Why don't you say how this relates to bisimulation?
Yeah, remind us what bisimulation.
I haven't gotten there yet.
So my understanding of bisimulation is that you can have different beta reductions and still you can say these processes or these executions are the same, although they don't have like you know step by step the same beta reduction or any other.
Yeah, so I mean, bisimulation is like it's a really general thing, right? It applies in any label transition system. So like any, you know, any set of states that you have this like you know, these transitions going to, you can define a bisimulation relation. And it's just kind of like a binary relation amongst the states. And you can do it with like different models too. And I guess that's kind of the point, is to say how two label transition systems are similar or dissimilar from one another.
So Greg said that strong bisimulation is in lockstep. Each step is in lock, right?
Yeah.
Weak bisimulation is that you don't have like this.
Yeah.
So what you're saying for this beta reduction, do you referring to more strict version, or you can have different beta reductions?
Yeah, so it's a little bit strange because so let's see, what are we trying to say? So beta reduction, you know, like term A, so I guess your terms would be states in this particular label transition system. So you have like vertices for your lambda terms, and then you connect, you know, you connect them with an arrow if you can do like a beta reduction from this guy to this guy, right? So then you have some transitions. And yeah, so I mean, you can definitely define different notions of reducibility or different reduction relations that would basically, you know, and then start asking questions about bisimilarity. So I forget what your question is because we kind of went on a tangent. But
okay, yeah. I'm not completely sure. Are talking about like you mentioned that they are the same as in alpha equivalence. So you know. I want to understand how strict you are in this relationship between, you know, this alpha and beta transforming to C.
Yeah, so I think the best way, in my opinion, is to not think about like individual lambda terms, but like when you say you have a lambda term, it's really a representative of an equivalence class of lambda terms, and that equivalence class is given by the equivalence relation of alpha conversion or whatever, right? So if I have some A and B and they're alpha equivalent to one another, then like both of those guys are just representatives of like the same thing, which is like that equivalence class of terms, right?
Yeah, so you're saying like when I have a function that I describe as lambda a dot a, like I don't really care whether it's A's or B's. Or what I'm really talking about is like this class, and probably what most people are talking about is like anything that's alpha equivalent to this term that I'm talking about also has whatever interesting properties I want to talk about.
Yeah, exactly. And so like if you apply that term to any other lambda term, like, you know, with the variable A or with the variable B or X or whatever name you want to give it, like they're going to beta reduce in exactly the same way. So it's like, it doesn't really make sense to talk about the individual, you know, lambda terms. It makes more sense to talk about like the equivalence class of lambda terms. And so then, yeah, I think then really instead of like individual lambda terms are the states, it would be like the equivalence class of lambda terms are the states, and then you have those reductions still.
So is there a thing, this just, I think you'll know this better than I do, Isaac, and probably Tomislav. Isn't there something called variable capture where like this actually matters? Like my lambda a dot a, it actually interacts in a weird way that I might not have seen with something just because the A's conflict or something?
Definitely, and I don't feel like I fully understand it. Like I think I can speculate as to what variable capture is, but I'm not 100% sure that I understand it.
Oh yeah. I remember like exercises in the K framework tutorial that I was able to do in the sense that he showed me what code to type and I typed it and I got the same result, but I didn't really like fully.
Well, yeah, but that's because the built-in substitution in K framework is capture free. So it takes care of that issue and you don't have to worry about it. But I mean, I think the point of the capture free substitution is like, if you're ever trying to do something like, okay, I have a lambda term and it's like lambda xy dot xy, you know, just something really basic. And then I want to apply that thing like to itself. Before I do that, I should just do alpha conversion on, say, like the second one. So I don't have any of the same variable names in these two things, because those variables have nothing to do with one another. However, if I don't change them and I just like directly substitute, you know, that second one into the first one, it starts to look like, oh, you sort of have like these X's in both of them, and like maybe that's an issue. I mean, but there are scoping rules associated with these lambda terms, you know, as well. Yeah, so I don't fully understand what the variable capture business is about. I don't know if Tomislav, you have a better idea.
Yeah, I was thinking, is this way you can change what variables are bound and what are free? Because in that sense, you don't have the same lambda term, right? If you have some bound variable, then becomes or you have a free variable and then somehow becomes bound because you put something else, then this is not the same, right?
Yeah. Okay, so yeah, let me say maybe my let's see, hold on, I'll share so I'm not just saying what I'm thinking.
Yeah.
Get rid of that, and we don't need to do this, but so I guess one thing that I found is Unicode support in Atom, which is kind of cool. So I can like actually use like nice symbols, which is really great. Except to search for them kind of sucks because it's like Alt L and then you type the name of it. It's just like a little bit horrible, but it's not so bad.
Let me just go one step further down that tangent. You know what else has really good Unicode support?
What's that?
Rust strings.
Oh yeah, okay.
Fun side fact.
Cool. So I'm thinking, yeah, so you'll see. I mean, this is like Alt L brings that up. And then the worst part about it is they misspelled lambda. Are you kidding me? They spelled lambda like this. But the other worst part is you have to literally type Greek as well, or else it doesn't come up with that one. So stupid. There's a B in lambda, guys, just so you know. All right, either way. So we're saying
submit a PR to Adam or whatever it is.
Yeah, right. You guys misspelled lambda. You know, so something like this would be like maybe my term. Oh, and one, you know, it's a little bit weird. I'm probably not going to be able to find the symbol that I'm looking for, but it's like a triple equality thing. And again, they don't call it triple equality. It's really weird. It's like this drama something. I'm not going to find it. Oh, well, it doesn't really matter. Just assume that this means like I'm just literally defining this thing as this thing. And then I have my term B, and let's say this one. So you were saying it's when I have a free variable in the term that's being, that's like the second one in the application. So, I mean, boy, even just like Y or something like that, right? And then I want to do, you know, A applied to B, but then like literally this thing is, you know, this lambda term, of course, applied to this thing.
So hang on, Isaac, I've got a kind of a dumb question about the syntax here. In term A, lambda xy dot xy, is that a single variable that's name is xy, or is that like short for lambda x dot lambda y? Yeah,
it's lambda x dot lambda y, and again, the best way is to just
copy paste it.
Yeah. So it's like that, right? And then you know, you can be even more pedantic than that and say like, oh, put parentheses around here, so it's like really super clear that, you know, this is a lambda term or whatever. But yeah, this is hand for that.
Okay, cool.
Yeah. So then something like this, right? Because then you do your beta reduction, which, you know, I have my symbols here, so I'll just copy that. And then put it here. So you do your beta reduction here, right? And beta reduction is basically like, I have a lambda term as the first thing, and there's some term here, and I can take that term and put it in for, you know, the first, and really it's this lambda term, right? So maybe I'll even use that instead. And then basically the whole deal is, you know, I can replace this X where it occurs here in this expression with this Y, but, you know, this looks pretty bad because I'm replacing, you know, a variable with something that's bound in the remainder of the expression, but now it looks like that's the same y, and it's definitely not the same y.
Yeah, that seems like exactly it. I think we figured it out, right?
Yeah, yeah. So then what's the, like, you just say, oh, but you know, this is basically the same as just putting some other variable z here, and so like I'm only ever gonna do this when the free variables in this expression don't match up with any of the bound variables in this expression, or something like that. Yeah. Oh, that's so cool. I literally never knew what they were getting at with this capture business, but
Yeah,
I think
cool. I'm glad we went through it. I feel like when like Gregory Russo like did it so early that I like wasn't able to appreciate what the hell he was talking about.
Yep. I definitely agree. Yeah, and so how do you appreciate capture-free substitution if you don't even understand variable capture, right? And I was just like, okay, this is a good thing. Like, you know, I ended up defining my own substitution function anyways because I didn't like the way that theirs worked, or I didn't understand how to tell it what to do, what I needed it to do. So I just ended up building my own. So. Yeah. Either way, that's cool. So this is variable capture. Awesome.
Okay, yeah, so like since we did this, like can I just make sure I know the calculus? So I remember that there's like three terms. There's like, you can say, I think they call it like a mention, like which is what you did on line 5, like it's literally just like a variable or something.
Yeah, yep. And what I was gonna say is lambda terms, right? Yeah, so you can, and you know, you can call it whatever, but you have some, just like in the pi calculus, you know, you have some list of names or set of names or whatever. Like you have some set of variables that you can use in lambda calculus, and so yeah, you can just declare one of those variables basically.
And then
that's one of the
prefix or something, lambda.
Yeah, and so now it's like, you know, if m is a lambda term, then you can do this, you know, you can do this application like with a variable with m, right?
Yeah.
Okay. So you build the terms inductively, right? Like you always have access to variables. Those are like the atoms in the language, and then, you know, given some lambda term, I can always then just, you know, do abstraction with that term as the body, basically.
And then there's application, I guess. Oh wow, you actually did all 3 of them already.
Yeah, and or, you know, m and n are, you know, both lambda terms, blah blah blah. Then this is like this is an allowable lambda term, you know, or you know, sometimes they put them in parentheses or whatever, but it literally doesn't matter. So let's do like that.
Cool.
Yeah. Yep. Yeah, that's it. I mean, and then and then beta reduction, you know, is this very specific form of application where your first term is some lambda expression, right? And so let's say beta reduction is that very particular form. Let's see, maybe I'll just copy this. No. And, you know, you got like an M here, and then it's being applied to an N, you know, space or no space, doesn't matter. And then beta reduction is this relation that says this thing, I can rewrite it after I, you know, put this symbol there. And it's basically going to be, I substitute this thing N for that thing X in that thing M, right?
In M. Oh, yeah, M. Yeah.
Oh, yeah. Right, cool.
Yeah, because M is like the body of the function, and X is the variable, and this is like the input, right? So it's like put N in for X in the body of the function M. Yeah, so that's it though. That's beta reduction. And then, you know, it gets this funky symbol if it can do this beta reduction. Yeah, and then we talked about alpha conversion. That's just changing the name of bound variables. So let's see, what step do I take next? All right, I'm gonna go to the notes and try not to dive in too deep. Sorry, there's a lot of notes. We don't need to talk about confluence or fixed point operators, but these are cool things that you could talk about as well. I would rather just jump right to representing computable functions. So one thing, and this is the worst place to look at it because I don't need this either. I didn't write a whole lot of detailed notes for these things because I just wanted to remember the ideas. So I'm just gonna go back up to like the actual definitions of everything. And again, like, you know, I slightly apologize here because I didn't think like, oh, what's the absolute best way to present all of this information? I was kind of just like, oh, I'll jump in and, you know, we'll start talking and hopefully I can communicate some ideas to you guys. So the first thing to talk about are these church numerals, because so there's this idea of like representing things as terms in lambda calculus. And when we start talking about functions, specifically the type of functions that we're talking about are from like the natural numbers to the natural numbers. Like, boy, if we could define that, we're off to a good start. So then the thing that we need to make precise is, well, what is a natural number in lambda calculus, right? Because we're only talking about things that are intrinsic to lambda calculus. So we're only thinking about, you know, variables and those abstractions and those applications. Like that's all we have access to. So what do we mean by something like a natural number? And so Church defined this notion of something called a church numeral. And basically, I mean, here's the definition of a church numeral. That's you know, and they're doing it in lambda calculus and combinatorial logic, like kind of at the same time. I mean, if you're familiar with this stuff, like you can look at it, but you know, things like, oh, what is B? I mean, I don't know. It's this nonsense that they define here. You know, it's like whatever. But
the SKI calculus. I never.
Yeah. They call it combinatory logic, and okay. with those combinators. And
so A is the definition of, this is how we're defining natural numbers, basically, right? The counting numbers.
Yeah, these church numerals specifically in lambda calculus, and B is, you know, in combinatory logic or SKI calculus, how we define them.
Okay, so like the number 1, I would define as like lambda xy dot xy.
Yeah, exactly.
Like the number 3 would be lambda xy dot xxxy.
Yeah, exactly.
Okay, all right.
Yeah,
I got it. Okay, cool.
Yeah, and specifically those applications are right associated, because if no parentheses are written, the application's assumed to be left associative. That's just like the rule of thumb, or, you know, that's the way things are, right? So this specifically is like, you know, resolve those inner applications first before you come outside, basically. But you know, the whole point is, and you know, this looks really scary now, but like the whole point is, this is some way of relating the idea of a natural number to a lambda term. And so the church numeral, and I'll just focus on lambda calculus, but the church numeral for n is basically just like, you know, n applications of whatever the first thing that you give me. It's essentially just it's a combinator, first of all. And by combinator, I mean there are no free variables here. It's like a closed lambda term. But basically what it does is it'll take 2 arguments, kind of like here. You apply this church numeral to the 2 arguments, right? It's some lambda term. Like, what can I do with lambda terms other than do abstraction over them or apply them? So you apply them to 2 things, right? 2 lambda terms. So F is, you know, the first one that's given to me, and basically it's saying like after roll beta reductions, you know, we get this thing F applied to X.
So this is an example of what you were saying earlier, when you don't write the parentheses, the application goes toward the left because we're applying that like n bar to f, and then x is still just sitting over there on the side.
Yeah, exactly. That's how we know like f is the first thing that I need to deal with, and then I deal with x, basically.
So okay. So yeah, so when you apply that to f, then you just put f in the position where y was.
Yeah. Yeah, so in some sense, there are like, I mean, there's only two beta reductions that are happening here, and so one thing that you will see if you look at stuff like this, okay, so this W thing here is for the reduction that's like beta reduction in combinatory logic. Don't worry about it, right?
Oh, okay, all right.
It's called weak reduction, and so that's why there's a W here. But beta reduction is really the only one that we care about. And so essentially it's like the first, so this is like a two-step beta reduction to get from the left side to the right side. And the first step is like you feed f into, this lambda term. And then you still have, so that took care of this x variable, but now you still have this variable y. It's still like an abstraction on the left side. So, this n bar f is still an abstraction, which then you feed x into. Right, and then it beta reduces to this thing. Basically, is the moral of the story, right? Like n applications of f onto x.
So this means we are creating that many nesting that we are counting.
Yeah.
This is where the result is.
Yeah. I mean, this is the definition of it, right? And
the x is always the same. We are not creating new variable in each nesting, right? We are just
yeah. This is this x and this x and x and this x, they're all the same, and all n of the x's that are there.
Yeah, this is just nesting.
Yeah, and it's just like repeated function application. Okay. So, that's what church numerals are. And so the point of me talking about church numerals is I wanted to make some sort of correspondence between lambda calculus and functions from natural numbers to natural numbers. And so the first thing was, well, like, what is a natural number in lambda calculus? Well, it's a church numeral, right? So anytime I'm thinking about a function whose like input is n and say like output is m or something, what I'm gonna want that to correspond to for the lambda term that represents the function is when I apply this thing that represents that function to the church numeral n bar, it gives me the church numeral m bar, if that makes sense.
Okay.
Yeah, and so unfortunately, one thing you can't do with Unicode is like put a bar over something. It's a little unfortunate, but so then it's like, okay, I gotta start using LaTeX if I want to type this out, and nobody wants to see me live code LaTeX, so I'm not gonna do that.
So when you say you are creating this transformation, this is not really like optimized, right? Because you cannot directly work with this lambda term, right? If you have number, I don't know, some big number, right?
I mean, you can't work directly with it. Well, so if the function has a particular form, which basically will be called recursive total, then what you can do is always just provide an algorithm for building the lambda term that represents this function. So efficiency is not really an issue in some sense, because it's just like, I don't know. You have this algorithm, you follow the steps, and like you'll arrive at this lambda term. Like, how many computations does it take? I have no idea. I can just guarantee you that it exists.
Okay, yeah.
Right.
This makes sense.
Yeah, so it's more of like an existence, like an existential claim than anything else. But yeah, so representability is kind of what we were just talking about. And basically they're saying like, okay, I have some function, you know, phi, and it takes n arguments, and even more particularly, it's a partial function. And so by partial function, we just mean like it's defined for some of these n tuples of natural numbers, and maybe it's just like undefined or doesn't exist for some others. And so basically what they're saying is like some lambda term x, and you can do the same analogous thing for combinatory logic, and that's why they were showing like the church numerals and for combinatory logic as well. To say that this lambda term x represents this function phi, we have to have several things happening. And so basically for any input that you take, like these n values, these n natural numbers, for this function to take those inputs and give you the output of p, which is again a natural number, is, and this is what I was saying, right? This is basically the same as, or at least implies, that applying this like thing that represents the function to the church numerals that represent those inputs in exactly that same order, somehow like through some like beta reductions and maybe alpha conversions and like going backwards with the beta reduction, you arrive at this church numeral that corresponds to p. And so this is this beta equality. And again, don't worry about the w. That's for combinatory logic. But the beta equality is like, you know, we can be doing beta reductions from left to right with some alpha conversions, or we can do some beta reductions from right to left, basically. So like we can beta reduce, or what's the opposite of reduce? Beta unreduce. I don't know. Beta build, right? You're either building or reducing. I don't know. So you can beta build or beta reduce, right? And end up at this guy.
I was thinking of some bio word like mitosis or whatever, where the cell splits in half to go back.
Oh wait, so it can beta reduce or beta oxidize, right?
Yeah. Oh yeah, that's a good one. Yeah. So,
yeah, but either way,
these are the two. Representability is part of the thing that you're building up to, right? The Scott Curie theorem. Okay, and this is the definition. Okay.
Yeah, and then the other thing. Okay, we didn't talk about normal forms, and maybe we shouldn't, because it's already like 1142. But for this function to not be defined, because it's a partial function, right? There can be inputs for which it's not defined. Basically, this corresponding lambda term like doesn't have this nice form, essentially. And so like no normal form means like you can just kind of like keep reducing it forever and ever and ever and ever and ever. And like this computation never ends in some sense.
Okay. Cool.
Yeah. So to be able to do this means that like this computation ends. There's like a bottom to it, right? And we want to say like, oh, in some sense that bottom is this like p thing. Yeah. Okay. And then, they go through all this stuff where they like build like, okay, we just said what it means to represent a function. Like, let's talk about the easiest function that exists from natural numbers to natural numbers, which is the successor function. So a successor function, has this formula, and they include 0 in the natural numbers, which, I'm okay with that. But basically then we're saying like, okay, here's the definition for like our ordinary successor function, and we want to find that lambda term that represents this successor function. And so the claim is that this is the lambda term that represents it. So this lambda uxy dot x applied to, u applied to x applied to y. Okay, what? Yeah, and so basically, I mean, the whole thing is like, so what does it mean for this sigma bar to represent the successor function? Well, it means that when I apply sigma bar to the church numeral that represents n, I get the church numeral that represents n plus 1, right? And so that's exactly what the claim is here. Like I can do this application and I'll do some beta reduction. And this is like, strictly just in that direction, right? And it could have gone in both directions because we had the equality up here, but it's strictly like just in that direction. I end up with this thing. We could go through that calculation if you want to.
So the successor function, for some reason, I was thinking when you presented the construction of the church numerals themselves that we sort of had already defined it like perfectly, like I felt like we had done the successor function somehow. Like the definition was we have the thing that's 0, I think we called it y maybe, and then like x, oh yeah, here we are. Oh yeah. Like this was somehow the successor function or something.
Oh yeah, I'm so glad you asked because so here's the thing, like and I can't do the bars over it, but I'll just do that, and that means like the church numeral that represents 0, right? And this thing is, it's that lambda xy business. This is the closest thing to it. That's fine. It's like lambda xy. Like x to the 0 in some sense, and I'll rewrite this in a second, because x to the 0 is just, you just don't write anything. So here's the church, the lambda term that like represents the natural number 0, right?
Okay.
And then we have the lambda term that represents this guy, and it's this. So that's what we currently have, and et cetera, et cetera, et cetera. Now the question is, I'm thinking of a lambda term, let's call it S, such that when I apply that lambda term to this church numeral that represents 0, I can somehow say that, okay, maybe it's not strict beta reduction, but it's beta equal to the church numeral that represents 1. So then the question is, well, what is this guy? This is a lambda term, right? Like, what is it? So, I mean, we have the definitions right here. It's just like S has to, when applied to this guy, and let me definitely put that in parentheses, has to somehow, through some sequence of like, beta reductions or oxidations, end up at this guy.
Okay, yeah, right. So that line 26 is like one case that we would have to be true in order to say that we found S.
Yeah, but we want so much more than that, right? Like we want this thing to also take the church numeral that represents 1 and gives us the church numeral that represents 2, and et cetera, et cetera, et cetera,
yeah,
right?
Yeah.
So yeah, we're asking for quite a bit here. But then the claim is that this S, and I don't really remember what it looks like, but I'll try to remember and then we'll go back to it. I think it was like U, and then I definitely don't remember who goes where here, but I think it's something like U, X, Y. So we'll see if that's close. Not that far yet. Here it is. U, X, Y, X, U, X, Y. I think that's actually what I wrote.
Yeah.
Hey, no kidding. Oh boy, just guessing. Yeah, and so then the claim is that this is the guy that does this stuff for every single N, right? So the claim is that like if I put the nth church numeral in, that I'll somehow be able to, through a sequence of beta reductions and oxidations, come out with the church numeral.
Gary put in the chat that it's called abstraction, beta abstraction, right? Isn't that what you said, Gary?
What's called beta abstraction?
Beta oxidation.
Oh, I like beta oxidation better, but whatever. Gary. All right, so by beta.
I like them both, actually.
You like both, yeah. Right. I don't dislike beta abstraction. I'm just biased.
Does beta oxidation have any relationship to chem lambda?
Well, no, probably not. Well, I mean, I really don't know. I just made up the name as we were talking. I was just thinking about like what is the opposite of reduction, and I thought of reduction oxidation reactions. I have no idea.
Yeah, nice.
Yeah, but so this is this, right? And
so line 32, the definition like sort of makes sense. So I'm reading. I'm saying like, okay, first you bind something to you. When you apply this to something, you bind the something to you, and then you just, like, it almost makes more sense in my other hypothesis for what the syntax meant that ultimately wasn't correct. But like, imagine applying S to something and think of UXY as being like a single variable that's called UXY.
Yeah.
Like you stop whatever thing it was in there and you put another X in front of it.
Yeah, exactly. Yeah. Yeah, so you just end up with this X that gets applied to this stuff, and like this stuff is somehow this thing, sort of, and you end up with like the next one, right? So and really by this thing, Can
I make a hypothesis? Like, what if, let me try another definition for S. What if like S equals lambda, I was gonna say, yeah, perfect. S prime equals lambda u dot xu.
Lambda u dot xu. Okay. Lambda u dot xu, right?
Yeah.
Xu. So I can already tell you that this can't work because I didn't write the definition of the church numerals down. These guys are all abstractions that take variables. So this thing is like this.
Mm-hmm.
Okay, and this is gonna look really bad, but that.
Yeah.
Let me put that around it. It's a little better. I think there's actually, you know what? I'm gonna take 1 second and find the superscript, and I know there's got to be one. You gotta have one. You're the worst.
Oh, it has some there. Hey. Nice.
There we go. So this is the church numerals, right? And so every church numeral is first and foremost an action with two variables.
Mm-hmm.
But this guy will never result in an abstraction with two variables. You would have to. Well, and the other thing is X is a free variable here, which is a little bit strange.
Yeah, that's what I was noticing. So what I was hoping or like thinking of this as was that you would bind onto like that entire thing that you wrote on line 31, which isn't really how those work, but like, I think that's what makes it really good notation, the way that you wrote it on 34, like where, lambda uxy kind of looks like a single variable, but it's able to bind something that has, two abstractions in it.
Right. Yeah, and like I said, we can go through this if you want to, but it's basically straightforward, right? Like you just place that definition in here, and you can show that basically what will end up is you'll add a 1 to the subscript by doing beta reductions.
Cool.
Yeah. Okay. Nice. So this lambda term is what represents the successor function. Okay, great. We're off to a really good start because we can represent like a really important function of natural numbers. And so the next step is basically we want to be able to talk about representation of like a wider class of functions. And so that class of functions, well, this is like the first step in that direction, is we start talking about these things called primitive recursive functions. And without going into too much detail, like a primitive recursive function is a function of natural numbers to natural numbers, or n natural numbers to a natural number is also fine. But basically, some examples are the successor function is primitive recursive. We also define the number 0 as a 0 argument primitive recursive function. So like, takes the unit as its input or whatever you want to think about. no arguments. And any projection function is primitive recursive. So like if I have, you know, n natural numbers and, you know, I want the case natural number and I just take that one every single time, then this function is primitive recursive. And basically the reasoning is like, well, I need a way to build up natural numbers. So, you know, I better have something like 0 and I better have something like the successor function because that's how I build my natural numbers. But we're talking about like tuples of natural numbers. So I want to be able to like extract individual natural numbers from those tuples. So projection functions are kind of in, you know, for no other reason. But then we have like composition of these types of functions are going to be stay within the same class. So like this class of primitive recursive functions is going to be closed under composition, basically. And so by that, I mean, if I take a bunch of primitive recursive functions and compose them in the right way, like I get a primitive recursive function. That's basically all there is to it. And then if I do recursion with these primitive recursive functions, then I'll get another primitive recursive function. And basically what that means is like, if I take the first argument as 0, that's kind of like my base case for my recursion. And that thing better be a primitive recursive function. And if I look at the k plus first, you know, step in this reduction or in this recursion, then I want to be able to relate it back to the case step. And so there's like some fixed function that relates my k plus first step back to my case step. And that's more or less what's going on here, right? Because we have like phi of k plus 1, and then some function that relates it back to phi of k. Yeah. I'm not 100% sure why I really need all of these variables in here, but essentially it means like, you know, the level of the induction step can factor into this computation, and also the arguments that you're using could also factor into it. Okay, you can do the same for the predecessor function, great. So the result then is that all of these primitive recursive functions are representable by lambda terms. Okay, that's like the next leap of faith, and so I mean that's exactly what I said, but even more so, like each one of these primitive recursive functions, which we call phi, can be represented by a combinator. You know, call it phi with a bar over it, and combinator is just that it's a lambda term and it doesn't have any free variables. Okay, blah, 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 you do some induction, who really cares? So I've never seen anything like this in lambda calculus, so I kind of wanted to show you some stuff like this, but they talk about this thing called the pairing combinator. This is the pairing combinator, and basically they're saying that this thing functions as like a tuple of, you know, the 2 arguments that it's going to get. Well, it really gets 3 arguments, but this thing, well, they're saying with like specifically with P and Q in here, is somehow like analogous to the pair PQ, in the way that if you apply it to 0, it gives you the first guy in that pair. And if you apply it to anything else, like for example, 1 would be just fine, then you get the second. These
are the accessor functions. These are like this D is the thing that you use. Like I've got a 7 tuple and I want the 4th element, so I take this and apply it to 4.
Yeah, this is like, you know, tuple dot 0 or whatever, and it's like, oh, okay, I'll give you that 0th component. And this is like tuple dot any other number, but 1 is like a perfectly fine thing to call it. So that's that. And then whatever, they start building this other crazy function. Let's not look at any of that. We don't need this. Recursive functions. Okay. And, you know, this is the next step is like, okay, we can do it for these primitive recursive functions. But even better, we can do it for recursive total functions. And recursive total functions a little bit more complicated to explain. But basically what they're saying is they're going to call, well, okay, it's a total function, right? Like, so total means it's defined for all n tuples of natural numbers. And recursive is going to mean
did you
that,
say n tuples of natural numbers? I thought these were being applied to, oh.
Yeah, because we're doing that sort of thing, right?
And what are the m's? Those are not just lambda terms. Those have to be, those are natural numbers. Well,
Yeah,
lambda terms of the form we defined already that we're calling natural numbers.
Well, so we're operating on the level of natural numbers right now. So this is just like, let's define the notion of recursive total function. So that's, you know, natural numbers to natural numbers, or n tuples of natural numbers to natural numbers.
Okay, so we're defining functions that take in like however arbitrarily many natural numbers and give out back a single one.
Yes, yes, and we're going to call it recursive, and we'll try to make some sense of that. We're going to call it recursive if there exists one of these primitive recursive functions. Well, okay, two of them. You know, psi and chi. Such that basically like the value that you get when you apply this function to those numbers is given to you by this primitive recursive thing applied to whatever this number is supposed to correspond to. And basically, yeah, it's like the least fixed point operator. It's horrible.
Oh,
This
wow.
is terrible. They just slid that in without saying anything. But for me, that was kind of cool because like the second we start talking about what a recursive function means, we're automatically talking about this like mu operator, you know. But they just give the definition right here on 2. I mean, they're saying, okay, well, first and foremost, there has to be at least some value of k that like makes this inside function equal 0. So like there has to be some value that works here. I mean, otherwise, you know, what number am I evaluating this psi at, right? But either way, so there's some value that works, and basically this mu k stuff means we're going to take the smallest value that works.
Okay.
Yeah.
Cool.
Yeah. Okay, and then the punchline is these total recursive functions are also representable as lambda terms. Okay, and then the real double punchline is you can do it for partial recursive functions as well, and basically it's the same kind of idea. Like they're representable by these lambda terms as well. Oh boy. All right, so we're at 12:02. I don't know what people are feeling. You can also get some stuff about normal forms, but who cares?
Yeah, I could stay for 10 minutes probably or so.
Okay,
I'm very interested in what we're doing.
Yeah, nice. And I'm trying to get, and we're here. We're in the Undecidability chapter.
Okay, cool.
Yeah, that's where I was wondering how long it would take to get to the undecidability.
Well, you know, I mean, we're 5 chapters deep in this book already, guys. Like 1 hour, 5 chapters. That's unheard of.
Yeah, good job.
Yeah. I'm gonna take a very quick bathroom break though. So hold on just.
Oh goodness. Okay, cool. Oh, yo, can you still talk to us while you're in there?
Well, I'm muted.
Okay, good idea. Yeah, I like that. Okay, so about undecidability, I had the Wikipedia article open. I wondered what it was that we were going to be deciding.
Yeah, I'm wondering also.
I think it has to do with whether something is recursive or not, but I'm not sure.
Okay, okay.
Oh.
Wikipedia's Scott Curie theorem says it's, oh yeah, he was talking about sets of lambda terms. So this is going to be about sets of lambda terms, I think.
So the Ackermann function is not primitive recursive, but total computable function.
Which function?
Ackermann function.
Oh, I don't know that one.
Yeah, it doesn't
before.
seem like it's covered here. That was I guess it can generate the basic arithmetic stuff without
Oh.
without recursion. I don't know, but that's for next time. For next time, maybe.
Yeah.
Like that. Function. Oh, with the C.
One of the simplest and earliest discovered examples of total computable function that is not primitive recursive.
Because that's, you know, the example that Marius Brillo uses for the graphic lambda calculus and the chem lambda, I guess to show its generality. I don't know exactly why, but it seems to be related to what you're saying
Yeah.
Yeah, they're talking about primitive recursive for sure.
Yeah, so my understanding from looking at this is that this function would be, oh, let's see, because it relates to itself. So it is itself the function that it's, oh no, I don't want to go back in the book, but I'll go back anyways. It relates back to itself. I'm so sorry. I hate scrolling through all of this stuff.
Yeah, maybe we should postpone this.
Yeah. So like with the total recursive functions, with the partial recursive functions, the function that related, you know, the next step to the previous step was basically some primitive recursive function. But if we're saying that this guy A is not primitive recursive and it is the one facilitating the recursion, then it's not even going to be one of these total recursive functions either. Yeah, that's interesting. I haven't looked too much into this Ackermann function. I've seen it before, but I've never really worked with it at all. Yeah, cool.
So, no, I was wondering if maybe you guys would be interested in getting Marius to talk to us. Maybe we could look basically at some of this stuff.
Oh, is this the chem lambda dude?
Yeah.
Yeah. Oh, that would be cool. I'd be interested.
Okay, because that's, you know, I was into chem lambda stuff before 2010, before I got into the pi calculus stuff, row calculus. The idea was this was sort of a natural computation that was local, whereas the row calculus is, you know, is global in terms of naming, whatever. And it seemed like, you know, the substrate of chem lambda, you know, was directly relatable to the natural world as so the challenge, the challenge would be to implement the row calculus with the chem lambda, or the graphic lambda calculus. But that's another story.
Chem lambda. I searched chem lambda and I don't think I found what you're talking about.
Let me, I'll put a link in the channel.
Okay, yeah, cool. Take your time.
Oh, so you were saying that you were wondering what we're gonna not be able to decide about, right?
Exactly. Yeah.
Yeah, so you guys were both on the right track. Like, there's something about recursion. There's, you know, some decision being made. But basically, it comes down to and so they're talking about this idea of like recursively separating sets of natural numbers, and that's very important that we're talking about natural numbers in this case. And so basically what it means to recursively separate sets of natural numbers is like we can find some recursive total function. So like one has that very particular form that we talked about before that only returns zeros or ones, and basically says for every guy from, you know, the set A, like your value is 0, and for every guy from the set B, your value is 1. Right? So it's basically deciding what set this element belongs to, right? Like which set do you live in? I can tell you by a 0 or a 1.
Yeah, makes sense. And the idea is that like these sets, okay.
It gets terrible.
Whose only output values are 0 and 1. So, okay, we're applying, okay, n is in A, one of the sets, if...
Yeah.
Okay. So what does it mean, a pair of sets A and B are natural numbers are called recursively separable if and only if there's a recursive total function phi.
Yeah.
So
how
would there, okay. So maybe the idea is like I could, if I just take a bunch of if I just take the natural numbers and split them into sets A and B, however I feel like,
yes.
Sometimes there'll be such a function phi, and if there is, then we'll call them recursively separable, but there'll also be other ways to set up A and B such that there is no such function phi, and we don't call them recursively separable.
Yes,
okay.
Exactly. Yeah, and so this, and the point is like this function phi has to be this very strict form of a recursive total function, and so it has to be recursive total, and basically what it's doing, what its job here is to say what set each one of these numbers belongs to, right? Its job is to distinguish like the boundary between these two sets in like some sense. Okay, but again, you know, we're talking about natural numbers and these like recursive total functions, cool, but that's not sets of lambda terms, and so now we have to relate things back to lambda terms, and you might think like, oh, maybe we want to use church numerals or something, but we don't want to use church numerals because we need the relation to go in the other direction. We need to be able to take a lambda term and give it a number, not the other way around, because we want to talk about in general sets of lambda terms, not just the ones that are like church numerals. Because it would be no different than just talking about natural numbers if we were only talking about church numerals. Okay, but so then the point is you basically, where's the best place to look at it? You basically define this notion called a Girdle number, and this, you know, x is just some lambda term. You know, they give some references for like, oh, you can find, you know, a Girdle encoding of lambda calculus terms that like has nice properties. And the two nice properties that we want this, you know, Girdle encoding to have are, okay, you know, bear with me here, right? Like, we want to be able to assign Girdle numbers to two different terms and somehow be able to relate through a total recursive function the assignment of those two Girdle numbers to the Girdle number of like the terms applied to one another. Like just totally horrible, but this is something that we need. And
stuff like that in physics, I think, like there's the in quantum mechanics they have the commutator, like can you apply no, maybe that's not quite the same thing. Yeah, anyway, go ahead.
Yeah, now I'm thinking about commutors and commutators. That sounds like a good band name. Either way, and then the other thing that you want is this relation between, and so just keep in mind, like this function tau is it's a function from two natural numbers to natural numbers, right? Like n squared to n, because I mean, okay, right there, you know, of natural numbers, right? Because it's taking in these Girdle numbers, and we want it to have this very particular relation between, you know, related Girdle numbers. And the other thing that we want is another recursive total function that basically relates n to the church, the Girdle number of the church numeral. It's just like mind bending. Like, what are we talking about? Right. So like we know some way to encode natural numbers into lambda terms, and we want that encoding to through this Girdle encoding to relate back to something we have a grasp on in terms of the original natural number. And by have a grasp on, I mean we want it to be this recursive total relation. Okay, so that is basically everything we need. Great, we have some crap. Okay, they make up new notation, right? It's like stealing x. X is a lambda term, and then we take the Girdle number, and then we take the church numeral associated with the Girdle number from that lambda term. This is just god awful. I mean, so this is
matching them, doing one to the other, and probably
yeah.
Guess,
X
right?
is a lambda term, and also sealing X is a lambda term, but it's given by a very specific thing, and it depends on your Girdle encoding. But then the bar above is just like, once you have this natural number, like give me the church numeral that corresponds to that natural number. It's just like,
okay,
how bad can this get? Bad. So, okay, whatever, they do like an example or something. We talked about the recursive separability of natural numbers. Okay, but what does it mean to be recursively separable as sets of lambda terms? It's convoluted, as you can imagine. And basically,
so we're taking all the lambda terms, filing them into two sets, A and B, seeing if there's a function that can separate them, just like we did with the numbers.
Yeah, and yeah. to mean.
So, well, okay, so we already know how to do it with the numbers, and we just invented that sealing thing. So why don't we take the Girdle encoding of each lambda term?
Exactly. That's exactly what we're going to do. So we basically say that a pair of sets of terms, lambda terms, is recursively separable if we can look at the sets of their Girdle numbers and they're recursively separable, right? But it's like, okay, wow, this is like, I really understand this. What in the world is the Girdle encoding, though? Like, how do you assign that number to the thing?
I remember you doing a sort of a weird thing like that with the row terms at one point, where it was like exponents or a couple low prime numbers and stuff.
Yep.
Yeah.
And I think it may have even had some properties like these guys. I can't say because I don't really remember, but
yeah.
Okay, and then so that's basically the whole story, and then we call some set of, in either case numbers or terms, decidable, or sometimes they just say recursive, if that set and its complement are recursively separable, right? So like, how do we take a property that's like a relationship between two sets and make it a property about a single set? Well, we say, can we have this relationship between the set itself and the complement of the set?
Yeah, or if they're allowed to overlap, which they're not in this case, you could say
yes.
like the set and the same set or whatever.
Yes, right, exactly. Yeah.
Oh, and is this what we're not going to be able to decide?
Yes.
Whether a single set is separable with its complement?
Yeah, it's horrible. So what we're saying is no pair of non-empty sets of lambda terms which have this property closed under conversion are recursively separable.
Oh.
So let's talk about the closed under conversion bit, because that's the crux. Like, that's the thing, right? Like, how could this possibly be true unless this is some crazy property? So the closed under conversion bit is basically like, if I have term in my set and I can get, from that term to some other term, which I call y here, through, beta reductions and abstractions, then that y, I also need that y to be in my set. So if we impose this property on our sets, this closed under conversion business, then we get into this Scott-Curie undecidability theorem situation, which says that I can't possibly produce two non-empty sets which have this closed under conversion property that are recursively separable.
Hang on a second. Closed under conversion, that's like approximately the same as saying like beta reduces? Or take one of these terms and beta reduce it, the result will still be in my set A?
So it's like the analogy I just thought of is it's like you know, like hiking, when you do a switchback, right? You can like go back and forth, right?
Yeah.
This is what beta equality is saying. Like, so I can start at x is like at the bottom, and I can walk to the right doing beta reductions, and then I can do beta
yeah.
to the left, and blah 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 blah, and I can do that, and anywhere in between I can alpha convert. Somehow I end up with this term y.
Yeah, I almost think of it as like going forward in time as doing some beta reductions, and then like going backwards in time to a maybe alternate path probably is
yeah.
Okay. All right, cool, I get it. Okay, so it needs to be, the set A, and we're going to take with its complement and see whether they're separable. It needs to be closed under this switchback kind of reduction abstraction thing.
Yeah, and I mean it's even saying more than that, because we're saying any two pairs of non-empty sets which have this closed under conversion property. It doesn't have to be the complement.
Okay.
So any two sets that have this closed under conversion property can't be recursively separated.
They can't be recursively separated. That means we can't find a function phi that will do the separating for us.
Yeah, and the proof is really cool. We're not going to go through it because it relates back to a bunch of old stuff, but I can give you the idea of the proof. The idea of the proof is basically, what are we saying? We're saying that we can't separate these guys recursively, right? Well, we have a bunch of representability theorems about total recursive functions. So we're going to use the fact that we can represent total recursive functions as lambda terms. And then the whole point is we're going to construct a term that's in both these sets that will give me both the values 0 and 1 from this function. So it's like, how can that possibly work?
Hold on, is it proof by contradiction? Is that what you said?
Yeah, you're gonna assume that you can separate them, and then you'll produce some term that will give you a value of 0 and a value of 1 out of that function.
And
yeah.
Oh wait, what does that mean? They're totally deterministic, right?
Yeah. So it means that assuming it has a value 0, you can show that it follows that it has value 1 as well.
That's the contradiction. Yeah, I see.
Yeah.
Okay. And so we never write down a concrete term that does that, though, right?
No, because you can take any two terms. So the way that they do it is, so they just choose any terms from those two sets. So like the term we construct will depend on these guys. But then like given those guys, we can write down explicitly what this term is.
Oh, interesting.
Yeah, it's totally crazy.
Wait, hold on. That's tripping me out, because if you're saying I can write that down explicitly, but we're never going to write down a phi. Oh, we're proving a phi doesn't exist because it would lead to a contradiction.
Well, so this capital F guy is the lambda term that represents this function phi, which we assume exists.
Oh.
Right? So we're like, pretend we have this function phi that does this thing that in a show is actually impossible. Like.
So here's what's tripping me out about it. Like, let's say like take a very concrete case where like, here are the sets, here is an A from A, I wrote it down. Here's a B from B, I wrote it down. Yeah. And you go through this procedure. It sounds like what you're telling me is we're going to end up with that. This procedure is going to generate both a phi and a term that you can apply phi to, and somehow it's going to give you a 0 and a 1. No.
We assume existence of phi, right? Because like we're proceeding by contradiction. So we make an assumption.
Okay.
And the assumption that we make is that we have phi.
Yeah.
But then we'll show that that can't possibly be the case, because then we get crazy things like applying this guy to this element gives me a 0 and it gives me a 1.
Got it. Okay.
Yeah. But here's the term that they build, J. It's this H applied to this weird, like I took my term and then did the Girdle encoding and then took the church numeral that is associated to that thing and then you know, I applied it like this, and here's H. I mean, it's just absolutely terrible, you know. But we showed, you know, I talked about D. D was that like that pairing thing, and
yeah,
you know, S represents phi. T represents tau, that total recursive function that related the two Girdle numbers to the application, and N is represents nu, which is that thing that related N to like the church encoding.
Yeah,
or the church numeral. It's terrible, just absolutely terrible. But you know, but point being is, you know, hey, here we go, we constructed it, because basically they show like, oh, if this guy satisfies some really weird recursive equation, then we can show that it has that strange property.
So what we can't decide is whether for a certain class of terms, we can't decide whether the term goes in set A or set B.
Yes.
Okay. Because in order to decide, we would need a phi function, and we just showed that there isn't one.
Impossible.
Yeah.
Yeah.
Okay.
Yeah,
cool.
So
I got to run out. Sorry to bail right at the end. That was very interesting. Thank you for sharing.
Yeah. Oh, yeah. Absolutely. Thank you guys for listening, because I got to explain this to somebody tomorrow too. So.
Oh, nice.
Or later today. Yeah.
Very good. Yeah, I'll watch this again. But why choose that book?
This is the book that the person who I'm tutoring is using. This guy is like trying to get through this lambda calculus book because he wants to work with lean. So he was like, I'm using this book, and I was like, okay, I will help you get through it. So that's my current tutoring task. Well, one of them.
It's very interesting. Now, I'm guessing that you and Joshi just went over the implications of this, but could you simplify the implications a little bit more for someone who almost understood what you were doing there? And
yeah. So a good thing to look at is like, okay, we proved some crazy theorem, and you know it's a crazy theorem because it has two people's names associated with it, right? So what I like to say is, anytime there is like more than one notation for something, or more than one name associated with something, we're talking about a thing that's really important, and you know how important it is by how many names or how many like notations you have for it. So like derivatives are so important. I mean, there's dots and prims and d by d x's and all of this stuff. And this theorem is very important because it has two people's names, and both of those guys are like really big names in this area. So super important. And then, so a good thing to look at is like, okay, we proved some crazy theorem. Let's look at the corollaries and say, like, you know, as like a normal human being, how do I understand what I just, you know, suffered through? And, you know, so basically what this first corollary is telling us is that if we take any set of terms A that's closed under this conversion property, and this is the like mysterious thing, right? It's this being closed under conversion that implies this undecidability property of the sets, basically. But that's exactly what this is saying.
Does that closed under conversion concept warrant a little more study, in your opinion, or just the hand wavy suffices for?
Yeah, it's a little bit hard to get a handle on it, because like I said, the definition of it is, you know, you have some term in your set X, like that term is there already, and now I want to tell you about another term that has to be there. Another term that has to be there, I'm going to call it Y. And basically, how do I know it has to be there? Well, I know it has to be there because I can get from X to Y by this beta equality thing. And the beta equality is like that switchbacking of like beta reductions and abstractions with alpha conversions in there. And there's just too many things happening, in my opinion, to like really, really fully understand what's going on there.
Okay.
Yeah, so there's something mysterious happening when we're allowing for these switchbacky paths by, you know, beta reduction and abstraction. But the point is, like, if we say any term that I can get to by doing one of these like beta switchbacks, that's what I'm going to call this now. By doing one of these beta switchbacks, that term also has to be in my set. So that's closed under conversion, right? It's closed under beta switchbacks. And oh, dang it, I did the wrong thing. I'm sorry. I scrolled down way too far. First. Okay, hold on. We're almost there. Oh no, it's terrible. Oh, we're here. So if we have one of these sets of terms A, and it's closed under this, you know, beta switchbacking business, then this set is not decidable. That's like the main conclusion, I guess. And then there's like an even further thing that you can say about normal forms, but we didn't really talk about normal forms, so I've just been kind of like pushing all that stuff to the side.
Yeah, I just wanted to say how this looks like choosing normal form. This closed under conversion, and I mean they say this is like equality, right?
Yeah.
This is like, it's not structure equivalence, but
yeah,
you can reduce if you have some term y and you can reduce it to x. I mean it looks logical that you cannot for sure say that you will have two different sets, right? Two separate sets.
Yeah.
Because these terms are almost the same, right? If you can reduce.
Yeah, and this normal form business is about if like I can't beta reduce any further, right? Like then my term is in normal form. Yeah. And so, I mean, you know, normal form is related to this beta switchbacking business because it's like at the foot of the beta switchback hill or whatever you want to say. I don't know if any of this is making any sense to anyone else, but so like a normal form is like the guy at the bottom of the hill, right? And like all of these other terms kind of like live on the hillside somewhere, and you can do, you know, you got a switchbacking path between them, and all of those guys have to be in the set. But
you know, I'm thinking what Greg now explains almost every Monday. He's I mean, this looks like he's talking about in more general sense how you even think about normal form, right? Because he introduced this R, which is like resource, which can and also the context, which can create normal form even if you have a redux, because you don't have resource to go further. Like you have a lambda expression, and it's still a normal form, but you don't have resource to go further.
Yeah.
And he's yeah.
Oh, I was going to say a similar thing can happen in lambda calculus, which is why I also talk about this eta reduction stuff too, because like there are some contexts where you would want to be able to do beta reduction, but you can't because there's like some application that needs to be taken care of before you can do the beta reduction. And so there are different notions of reduction. Like beta reduction is not the only one. There's like eta as well, and some other things that you can say about these you know, these calculi. Yeah, but that's cool. I didn't think about the relationship between the proof theory stuff that he was talking about and what I've been reading about regarding lambda calculus.
Yeah, I'm thinking that this D and Greg's duplication.
Yeah.
Because in Greg's representation of well, he was explaining how he created new names, like separate names that are not part of so in each nesting, like we can create completely separate names that are not exist in any other branch. And
Yeah.
I'm thinking that maybe this D is similar because you somehow creates two branches, and you then you can definitely say, oh, if I don't have, if I cannot find the common parent or something like that, I can really say, oh, I have completely separate sets.
Mm-hmm.
And
Mm-hmm.
but if I have this parent from which I can reduce, or maybe not the parent, but I have the same term from which both of these terms can reduce, then I cannot decide, right? Because everything is possible. They're really the same, right?
Yeah, I mean that's basically what that undecidability comes down to, right? Because to have two terms that beta reduce to the same guy means that those two terms are beta, you know, equal to one another. And so if one of them is in the set, then both of them are in the set, and then now we have this, like, you know, impossibility of deciding on our set because we have this like equality of all these reductions.
So this D really is doing this separation, right?
Yeah,
you're creating something that you say, oh, now you don't have this common term that you can reduce, and
yeah,
this is the proof, right? Or
I'm not 100% sure, but I like that you're saying that D somehow relates to branches, because like they even use a notation that's like, you know, when I apply D, so it gets applied to three things. The first two are always called like X and Y. And the third one, typically they just use a church numeral because that's, you know, kind of like the meaningful case to apply it in. And then basically an alternative notation to writing like D, X, Y, church numeral is if the natural number n equals 0, then X, else Y, right? Because that's exactly the property of that D combinator.
So I'm thinking that this is maybe very simplified R, what Greg is saying, right? Like this is very simple language for research, because you're just saying, oh, I have 0 and 1. So, you know, you can have the whole language for this R, and you can express who know what.
Yeah.
You know, I'm thinking that it must be that, you know, Greg is presenting something that is even more general. So it must be that, you know, we should see how this is implemented, or how this is visible in you know, previous papers related to lambda calculus.
So now I'm thinking like D is basically a binary resource, right? Like there's only two possible ways for it to go, but you know, the resource that Greg wants to introduce is like more complicated than only two values.
Yeah, and it must cover all of this previous stuff, right? Because it's more general. So
and maybe that's the connection, right? Is if you can constrain his resource to something that can only be a 0 or a 1, for example, then like basically we should be able to produce something that's very similar to what's happening in lambda calculus.
And this reminds me to dependently typed implementation of a vector, or like a list with specified length, where the length is natural number defined on the type level, which is exactly that, right? It's it can be 0 or successor of natural number. So and it is used in completely the same way. When you want to define a vector, you're saying, you know, how many nesting of these natural numbers I have.
There's so this is the book that I'm using, Lambda Calculus and Combinators, Hindley and Sheldon. And I just wanted to show you some of the later material in here, because they get, you know, into like simply typing with you know, in lambda calculus and in combinatory logic, and there was something about dependent function types. So I'm very interested to get to this section and maybe understand what dependent typing really is, because I still don't have a good grasp on it.
Yeah, I mean, when you showed these lambda expressions, I was trying to figure out how can I imagine this with not only with functions, but right, because we have data types, and how can you define data type that is a co-product, right? You can define it with functions, right? You have two cases. One will be the function that is like unit, and the other one will be the function that accepts well, I'm trying to figure out from defining Boolean algebra with functions, right? You have higher order functions that you can decide. What did you receive, 0 or successor, and then you go further.
Yeah.
I don't have it clearly now in my mind, but
yeah.
You know what I think? In Haskell, you can say data nat equals to 0 pipe successor of nat. This is just the data type, but it must be implemented somehow with the functions, right? There is no other way. So
right.
And
Yeah, and I think I mean, I don't know. I don't want to say everything is like that D combinator, but something like that D combinator may be able to do it, right? Because we can say, like, for that like that case, the constant 0 that we want to define, maybe that's just the output of this thing when we give it the number 0. But it's a successor if it gets any other number, basically.
Yeah.
But I don't know.
Yeah.
I don't
know.
And
that is exactly how independently typed language you have these natural numbers functions on the type level. So you can say if you have two vectors and you want to append one vector to another, you just also you also summarize the natural numbers that are part of each vector. So this is how you have length of one vector. You just sum it with the length of the another, and that's it. You have on type level. You're preserving, like church numerals implement representation. Although this is not really represented as a church numerals, because it's just optimized to work with normal numbers.
Okay.
This is why I asked you: do you really mean like real representation or with the lambdas, or your mean? Yeah, it's possible, but in real life, I will use like.
Oh yeah, definitely. Like they're not doing this stuff in like an optimized fashion. It's just like, okay, how can I define the least amount of things and be able to talk about the stuff I want to talk about?
Because in Idris, for example, the notation and data types are really as data types, but the real calculation will not be like that, right? It will be translated to normal numbers, and it will be fast.
Yeah, man. I really want to start learning some Idris or Agda. Those are like, I would be very happy learning either one of those. And I guess since Agda is closer to Haskell, maybe that's the one that I should work with. But
well, Idris is closer to Haskell.
Idris is closer to Haskell.
Yes.
Oh, okay.
Yeah, maybe we can have one session for Idris, and because in Visual Studio Code is really usable now for Idris. So
Oh, cool.
Didn't Dan give us a introduction to Idris once?
Yeah.
Oh yeah, I was on one session when he was translating this paper, this special language that they use in Agoric.
Oh yeah, yeah.
Translating this to Idris, and that was
Oh,
yeah.
cool.
No.
No?
No. This was another thing. This is something that is back then it was not published, so I'm not sure if it's published now.
Yeah,
but
right. That's right. I remember that.
Yeah. So yeah, his translation to Idris it was great.
Yeah. Okay.
And also in Atom there is a plugin, and I think it works pretty good for Idris.
Oh, I didn't know that Atom had a plugin. That's awesome.
I mean, the Emacs is the best, but some common shortcuts works also in these editors, because you definitely want to have these special commands where you can say to Idris, generate all the cases, and
Oh yeah.
these things are very important, because you don't want to write everything.
Yeah, I was gonna say, does Haskell have something like that? Like when I make some function that takes a data type that I just defined, and or even I didn't define, but it only it's a co-product, so I want to do pattern matching. Like, is there a way to just generate all of those cases instead of having to write every single one of them? There should be.
I'm not completely sure, but I think there is nothing directly in the GHC. Maybe there is some kind of additional library or something that you can use, but I didn't see anything inside the GHC.
Okay.
The only thing you can do, which is helpful, to specify the hole, and then you can say, oh, give me the type of the hole, and then
you can.
Yeah,
and that you do in Haskell with the undefined thing, right?
Undefined, but or underscore. Then you can specify
that's
the hole.
right. I haven't used that very much, but I do remember learning about it at some point.
But if you have like good plugin for editor, then you really don't need all. You don't need it in this form, because you can mouse over your term, and then you see the type. So you can really pick the whole whatever you want. So it's much nicer also.
Yeah, cool.
Especially if you want to find the type inside the body of your function, then it's great that you can just put your mouse there and you see the type. And I'm using this also in Scala to find the type, because
I haven't, I don't know what it is. I need to look at my dependencies or something for my Haskell plugin for Atom, but it never works. I don't even know.
I'm starting to like Visual Studio more than Atom. I got Thomas Love's Rolling plugin going.
Yeah, that's really nice.
In no time with Jim's help.
Yep. Yeah. Sweet.
I mean, I don't want to advertise some editor, but it's Visual Studio Code. It's much more mature, and
than Atom. Yeah. I definitely run into many more dependency issues with Atom than I do with VS Code.
And one additional thing is that Atom is built in GitHub, right? They were starting with, and Visual Studio Code is for Microsoft. So now Microsoft owns GitHub. So
what's the point? That's funny. All right, guys, I got to get running here. I got some tutoring to do in about 12 minutes.
Yeah.
But hey, thanks for joining and listening and asking questions, because it always makes me understand things better when I explain them. So
Well, thanks for sharing, because I
Thanks.
learned a lot
Yeah.
this morning, and
Yeah,
it's a
awesome.
very, very interesting subject.
Yeah,
Yeah,
cool.
yeah.
I think so.
You're always connecting so many different things, and that's great.
Yeah, good. I'm glad you're finding some value in that, because most of the time I'm like, oh, it's just like a totally stupid connection that I made. Like, there's no value in this, but yeah.
Oh yeah, always.
Yeah.
I think I will have some questions for Greg in Monday.
Oh yeah, nice. Yeah, I'm gonna try to start going to that. There's been like the last several weeks I've had some conflicts, but hopefully that won't continue, so I can come back to the cast.
Oh yeah.
Good.
Yeah, that would be great.
Cool.
Thanks.
All right, guys. Good
See
seeing
you.
you.
Bye.
I'll see
Bye-bye.
some of you guys tomorrow, hopefully, for the category theory stuff.
Yeah.
I hope I
I'll be
have
there.
something ready, but
Yeah. Awesome.
it's not going to look anything like what you just did.
Oh, that's totally fine. Don't know what is the saying? I don't know. Maybe this is not a real saying, but comparison is the death of all progress, or some is the poison of progress. I don't know. Some make up some saying and then live by it.
Okay.
See you.
Yeah.
Bye-bye.
Thomas, can you stay a minute?
Yeah, sure.
I just I noticed that it was saying it was waiting for our node. I don't know how to hook this to our node, and I guess.
Can you please say what? I'm not sure that I understand the context. What you saying?
Well, I'm trying to figure out. Well, first of all, can I use this for debugging? I mean, this is not simple code here, so I don't know if I can do it or not. But I just don't know how to use this for debugging. That's all. Should I start a new file?
First, let me. Can you tell me what do you mean by debugging? And what do you want to debug?
Finding syntax errors, for example. So.
So you want to execute your role.
If I do something like this.
Okay, you can. If you save the file, it should be executed and show you the error. We only need to do is
that an error really?
Yeah, this should be an error.
Okay, and then I do a Control S to save it. Rolling is started. Please wait.
So so can you open the console? You can go to, I think, view and output. So in output, you can select here the tasks, but you need to select rolling, because you want to see rolling extension output. Here is the all output that you want.
Thank you.
Something failed. Something failed. Something failed. I'm not sure what. Invalid mode. Did you change anything in settings for rolling plugin?
I changed it to Docker.
Can you open the rolling settings? I think the shortcut is Control comma. And now you enter rolling, so you will see rolling settings. Yes. And can you now scroll down a little? So this is fine. Oh, everything is default. Oh, you switched on all output. So
I switched
yeah,
on
this
all
is fine.
output.
Yeah,
and
this is fine. So
I switched
you
on,
want to see everything.
I switched on Docker.
Yeah, okay. So everything is fine. I'm not sure why Docker is not working. Invalid mode VS Code / VS Code.
The response could be invalid mode / VS Code.
So you're running this on Windows. I tested on Windows, but maybe I introduced something that I'm not aware of.
Okay, so
can you go to the console to the terminal and just that we check if your Docker is fine.
I don't see anything under here.
So this is
what
fine.
What should I type? Docker.
Docker run. Let's try just run you know, standalone node just for test. So Docker run.
Okay, so I should find all the arguments we need.
Yeah, I will tell you. Docker run / rm. This is for it's just a temporary node, so you don't need to delete it after stopping the node. So --rm.
--rm. What?
Yes.
And then I do rchain.
No, not n, but m.
What do I want?
So let me put this in the chat. So maybe Docker run rm it. Now I need to specify rchain node and /s run /s. This should be the command. Let me try on my machine so to be sure. Yeah, this should start the node.
I don't understand how we're getting the audio.
You're getting my audio?
Yeah, I heard a little. So this is working. So yeah, so this is working. So maybe there is some kind of bug that I'm not aware of. Can you restart the Visual Studio Code? You can do it. You can select the command. Control-Shift-P will open the command window in the Visual Studio Code.
I don't see how he's running two Zooms at the same time. I guess he has it on another computer.
You can open the command with Control-Shift-P. No, I don't want the terminal. I want the command. This is command that you are supplying to Visual Studio Code.
I guess you can do that right on.
I'm not sure that you have this in menu.
I don't know.
Can you try keyboard shortcuts?
Try what?
Can you try keyboard shortcut? Control-Shift-P. Yeah, so now you're in command mode, and now you can type reload, and you will see reload window command.
What do I
please type reload? Reload.
Oh, reload.
Yep. So you can directly call command, and you see the second command is the reload window.
Is that what I want?
Yes. So this will restart Visual Studio Code, and now you need to select rolling file to start extension, to start R-Node in the background. And now open the output window, output console, so that we can see what plugin is doing. It should switch to rolling. If not, you need to select it. Yep. Okay, it seems that it's starting, but yeah.
Okay, now.
Yeah,
it could be.
It seems that this is some kind of error.
It's.
I need to check how this works on Windows. It seems that it's some kind of problem.
All right. Well, we'll see.
Can you just check?
Code, /VS Code sounds like a Windows option.
This /VS Code is probably something that I'm supplying as a parameter to Docker command, and this is something that is not accepted on Windows. But can you just type Docker version so I can see what version do you have?
I guess I can kill this.
Yeah, you can. Yeah, you can. Shut down. Oh. Are you using Docker Toolbox or you are using Docker for Windows?
Docker Toolbox, I guess. Yeah. I'm not very familiar with Docker. I guess I gotta get more familiar with this. But,
so you have version 19, but Docker Toolbox is old version of Docker for Windows. I'm definitely not checking Docker Toolbox. So I'm definitely expecting Docker for Windows because this is the version that is now official.
Docker for Windows, huh?
Yeah. I didn't know that Docker Toolbox still exists.
Well, that's apparently where I am, Docker Toolbox. Right, I assume I just load this again. This is that, have you seen the lambda stuff? This is the acronym function. It's
yeah, I remember that I was reading about lambda when you mentioned it.
Right. That,
I'm still seeing lambda as very low-level graph oriented.
Yeah.
Which I think is very difficult to work with. You know.
That's true. Yeah. So.
I mean, it makes sense, but when you go to the graph level, things are very complicated. So
does the Docker for Windows require the native
Hyper-V
visualization?
Yeah. Yes. You need Docker for Windows needs Hyper-V.
Yeah, I don't have that.
If you have, I think it's Hyper-V is only on professional version or something.
Right.
Yeah, I didn't. Yeah, no, I cannot tell you. I cannot tell you if the error is related to that because I didn't check with Toolbox. It's yeah. But I will see if I can find out what is the problem.
Is there an alternative to running Docker? Can I run with a remote node?
Oh no! I mean, you can use your Yeah, but you are on Windows, so yeah, Docker is the only option. Sorry. Yeah. You cannot have it installed, right? Because yeah. Yeah. I will check on Windows. So maybe you can use Docker toolbox. But you know what is the problem? The problem is how Docker is mapping host file system to container. Yeah, so I need to check that. But if you can try with Docker for Windows. Maybe.
Is /VS Code a Docker option?
No. This is something that I can easily check for what I'm using this. Yeah, but I'm just creating, referencing the folder that is mapped